So this session will be recorded and later on put on YouTube on a limited channel or unlisted channel for you to access if you want later on. So are there any questions before we start with our new topic? So, okay.
Hocam, boyutlu struct'ı pointer'a nasıl atıyoruz?
Ask the question again. I don't understand it.
Boyutlu struct'ı, mesela bir struct boyutlu olacak. Pointer'a atanmak için, pointer gösterimi yapmak için.
We are going to talk about that in depth today, but when you say boyutlu struct, what do you mean? You mean array, structure arrays?
Evet, evet.
Okay, so we'll talk about those in depth in the coming hours, but so keep your question for the time being. I'll talk about that today and tomorrow, most probably. Okay, so folks, we are gonna talk about today the dynamic data structures, and this will take probably at least a couple of weeks, maybe like a total of 8 hours, maybe a little bit more. So this is an important part of C programming language, very useful, I mean, it actually helps us do a lot of things. So you'll see quite a bit of use of it. And it is rather one of the probably the most difficult part of if you consider learning C difficult, this will be the where that difficulty is going to be a little bit at least. So more difficult than the other parts, but not necessarily impossible to learn. So it is easy enough, and we'll go through this thing so that you get it hopefully easily. So one of the needs for the dynamic data structures is actually clear. If you recall what we have done so far, we assume that all the, let's say, data that we have considered in our programming so far, they are limited in their size. So we have, let's say, when we define a structure and we define a variable to hold a structure type like that, we have either one of them, one copy of such data, or maybe a few of them in an array. And even in the array case, we'll have the fixed number of a sort of a predefined fixed number of those things. And this is quite restricted in use, of course, because we actually have a lot of, let's say, need for changing data size, changing, let's say, array size might be 5 in one application, and it might be, let's say, 1 million in another application. And if I need to keep everything in a very large array, then I am wasting my resources. I am wasting my memory for unused or not unused stuff, right? So a lot of programming will require things, your data, your, let's say, variables and all those things to expand and contract as your program runs. So it may not be fixed, and in most cases it's not going to be fixed. You'll have changing, let's say, size of data that you'll be your program will be manipulating at any given time. So both expanding and sometimes also contracting. So the changing data size should be actually possible. And so the decisions on space, meaning space for memory or memory space to keep your, let's say, data, is made during the execution. So in this case, it should be done during the execution. An array is, the decision is actually in an array definition, decision is made beforehand. When I say, okay, I want to, let's say, use an array of something, what do I do? I say, I declare something like this, right? I say, okay, integer, some array, and some size that I need to define here, right? And once I do that, and this is during the compile time, I do this one during writing the program. Once this goes through the completion process, then I cannot change this number. If this is, let's say, 100 here, then my compile code cannot have more than 100 entries for this particular case, right? So this is very limited. So we want actually to have somehow this dynamic memory allocation. I want to be able to say in part of my code during runtime, I say, okay, I need an array of 100 integers. Or maybe at another time of that same code, I may say, okay, I need an array of 1 million integers, or maybe 5 integers, maybe whatever, right? So the question is, how do I handle this type of a need? So you cannot say, okay, make this 1 million, right? And hope that you can use as many as you want during the runtime. This is not efficient. 1 million, when I put, this is 10 million. So this is 1 million, this is fine. So when I actually have, let's say 1 million entries there, I am keeping, let's say 4 megabytes of my memory for this purpose alone, or for 8 megabytes of my memory for this purpose alone. And this is not desirable because in some cases I may need 5 of them, in some cases I may need 100 of them, and maybe rarely I may need 1 million of those. So there has to be some way of dynamically allocating memory per need, which is defined at runtime, not at compile time, right? So this is what we are going to discuss in the next couple of weeks. How do we do this dynamic data management? How do we actually have dynamic data structures that can change their size during the completion, not during the runtime, not completion process, after the completion, during the runtime. All right. In order to address that, we have to revisit our pointers topic. So the way that C actually helps us do this is C says, okay, I'm gonna let you do this type of, let's say, dynamic allocation, and this will be handled with a pointer type, a specific type of data or value. And we have discussed this quite a bit. We are going to get a little bit deeper into this one, and we'll look at pointers for, they will be the base for dynamic data structures. And if we review what we have done so far, we have used actually pointers for mostly referencing and indirect access. So where did we do that? We used this for, let's say, in functions calls and in some other places where we actually know how to actually reference and how to actually indirectly access to a, let's say, to a memory or a variable's, let's say, content in memory. So let's review how that worked. So this is very simple. I assume that I have, let's say, I think this is an integer. I have an integer num. This is declared. So num is declared as an integer. So I know that this is supposed to have a thing in the memory, a space in the memory. So this box actually represents the space. And this space will be able to hold a 4-byte integer in it. Okay. And then we have another one. This is a pointer, integer pointer. And the declaration was, if you recall, the type followed by a star and followed by variable name. Now, this variable I don't want to do this one. Let's change this one here. That one. So let's call this num_p, meaning number pointer to number, right? So this is the name of the variable is num_p. This is actually a pointer type, and we know that this is saying that this pointer, this variable num_p, N-U-M-P, will actually hold an address, which can be used in turn to actually indirectly access whatever is in there. So if I actually, let's say, do something like this, num_p equals the address of num, for example, here, if I do such a thing. So num_p is a variable which is supposed to be keeping an integer pointer, right? So this is what it is designed for here. And num is another variable, which is actually an integer. And this address operator, the ampersand operator, is actually is the C's way of actually letting us access the memory where num is actually is kept, whatever the content of num is kept, right? So this address now is actually inside in num_p. Num_p is pointing to, it is actually a name for an address in or a space in memory, and there is something in that memory address or the memory place or that slot, right? So that is the address of this num, which is actually the content of it is gonna be 3, right? So num is the direct value of num. Num_p is the direct value of num_p, the address, and in this case, address of num, and star num_p is actually the indirect value of num_p, meaning that I am actually gonna be looking at the content of num_p and use that as an address and get the value of that at that address. And then in this case, you can see that the value of num is 3. The value of num_p is the pointer to the location of the address containing that 3. And the indirect access to that or indirect value of num_p is going to be whatever is contained in that address. This is the indirect value of num_p. So let's have a look at a few different code segments, how this thing works, so that we can refresh and maybe a little bit understand what is going on, right? So here you have a simple code. So I have what do I have here? I have a variable called num, which is an integer. So in its memory, somewhere in the memory, now my compiler knows that num is actually the name for this address or for this space here. So this space here can be accessed by just using the name num. Okay, now here I can use this name as a left-hand side operator to an left-hand side operand to assignment operator. So when I do this one, it will place number 3 here. Okay, this is the first one. The second one is here. It says now I have another variable, which is actually supposed to be holding an integer pointer. So integer pointer means it's gonna be an address. So num_p is another space in the memory. I don't know where it is. I don't care where it is. Compiler gives me that. And the content of this is gonna be address. And this address is this is gonna be the content can be only an integer address, an address to an integer value, wherever that is. So in this case, this particular thing here at line number 9 is saying that take the address of num, which is this place here, this address here, and copy this address to where is numpy kept, or numpy's memory area. So this is gonna be, in principle, what's gonna happen is that this guy, the address is gonna be copied here. So this guy is gonna be pointing to this one. So let's see what happens here. What I did is I am printing the num. I am printing the numpy, which is the pointer, integer pointer, which means that there has to be an address in numpy. If it is assigned, if it is initialized, there has to be an address in numpy, which should be pointing to an integer value, okay? And then this is the indirect value of that one. I can actually use a star in front of this pointer to get to that address and get the value from that address. So it's clear that num has 3, right? So this is the output of this code. Num is gonna be 3. This is very easy. It's obvious, right? How about numpy? Okay, let's look at numpy. Numpy is supposed to be the address of where this value 3 is actually kept. And in this case, the address is here. This is a big number, and printf has an option. This %sign p says that my number, my value that I want to print is actually a pointer. It is an address. It says it's an address. Now, in printf prints these addresses, this type of values, in an hexadecimal format. So hexadecimal format means that I have, let's go back to here. Hexadecimal format means that I have a 0x here, and then afterwards I will have hexadecimal numbers or digits. And how many do I have here? Let's see. I have 2, 4, 6, 8, 10, and 12. So I have 12 hexadecimal digits there. So the question, I will ask you a question: how many bits do I need actually for this particular thing to be represented, or memory? How many bits in this thing? So each of these have 4 bits. So each couple will actually be bytes, 1 byte. So I have 1, 2, 3, 4, 5, 6 bytes here. So this is a 6-byte address. Okay, good. Now, this is the address. This is apparently, I know that this is the address of where that number 3 is actually kept. So if I look at the address here, perhaps this address was 0x7 something 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 954, where 3 is kept. All right. So this is what it is saying. This is saying this. Why do I say that? Because numpy is initialized by the address of num, where that number 3 is kept. Okay. Now, when I actually try to access address, the value, indirect value of numpy, meaning I go, numpy is here. This is numpy. And numpy has 0x7 something 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 954. This is what it is inside in that place. And when I say start this, it says take this address, go there, and get the value from there. What type of a value is this? I know it is an integer value. Why? Because numpy is defined as an address to a pointer to an integer value. So this is the definition. And here I did this right because I got the address of an integer variable, put it in an integer pointer. So everything is perfect here. There is no issues here. Therefore, I know that star, or the compiler knows that star numpy is gonna be an integer because this was an integer pointer. So whatever this numpy is pointing at is indeed an integer. It must be an integer because this is the definition. So how do I know that it is an integer? by definition. And then how can I actually make sure that the programmer put a address there that is pointing to an integer? This is because of this guy here. The address of num is gonna be an integer address or integer pointer. Okay, so this is very simple. Any questions? Let's see. By the way, okay, there are some questions, I guess. No, people are. Okay, num p değiştirdiğimizde num da değişiyor mu yoksa? Okay, nice. This question is, what if I change, let's say at some point here, let's say that the question is, if say that I have another variable here, let's say x, all right, and x is 4, and I say here num_p is the address of x, all right. So in this case, changing the num_p doesn't do anything to num. So this is the first thing. This is good. Now the question is, I think, is this one. It's saying, okay, if I do it this way, let's say num, ugly. So the question is, if I say here, let's say before this one here, I say star num p equals 5. What would have I gotten at the end? What would I get at the end of this call? What would I print? So let's see what's gonna happen. So this is what we have. So first, num is here, and it is filled with 3. Okay, this is at line 8. Line 9, now num_p is having this address 0x, this is 0x x something 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 8954, and then I have it here 8954. Okay, now at line number 9, I actually got the address of num, which is 0x7FFF35CA8954A, and I put it here in this place here. Okay, and then at line number 10, I'm saying, okay, go look at num_p. Num_p is this address. Get the so now what this is telling me is that do an indirect access to this thing. So look at the num_p, get the address of num_p, go to the place where actually it is pointing at. Now I am here. I'm pointing at here. Star num_p is actually pointing here. Now I said, okay, assign to that place 5. What's going to happen? Of course, what will happen is that I'm going to overwrite this with 5. Now, once I actually print this, num is going to be what now? What is num going to be? If I overwrite 3 with 5, num is then 5 as well. Num_p is the same address, it doesn't change. And then star num_p is also 5. So the answer to your question, let me see who was the owner of the question, Atakan, is yes, if I change the content of star num_p, I will be changing the content of num as well, because they are pointing to the same place, right? So this is the idea with the pointer, and this is the idea, if you recall, with a function call with a pointer. We were actually sending this guy to the function so the function can fill it in. This is the same thing here. So I am able to actually change the thing. So in principle here now, because of this thing, num and star num_p means the same thing. Star num_p and num means the same thing. Wherever I can use num, I can use star num_p, either a part of an expression or as a, let's say, left-hand side operand to an assignment operator. All right, so this is clear. Okay. Any other questions? So let's look at it here. Am I recording? Yes, I am recording. Okay, he says numpy num ile numpy aynı anlama geliyor mu? No, of course. So the question was simply, is this? He's saying, if I say numpy equals num, what does this mean? At what line, of course. So I think the question, the owner of the question should tell me, where do you want to do this one? At this, first of all, let's look at this, what this means. This means that I am taking the value num, which is, let's say, if I am, let's say, here at line 7. No, not line 7. Let's go back to this one. Let's go erase them all. And let's say that replace this guy with star num p equals num. So what would happen in this case? It says take num. So the assignment operator says, okay, get me your right-hand side first. What do you have on your right-hand side? What do I have on right-hand side? Num. What is num? Currently 3. So this means that this is 3. So, okay, now right-hand side is handled. What is on the left-hand side? The left-hand side should have a place and a kind of a place, a memory place, where I can actually store this number 3. Is it a memory space? Yes. This is how do I know that? Okay, at least theoretically this is a memory space. Why? Because numpy is an integer pointer, and star numpy should be pointing to an integer wherever you are actually, you can hold an integer value. However, if I don't have this line here, numpy is not initialized. So I have this one here. Num is here. This is num, and this is numpy. And right now, even though num is initialized, numpy is not initialized yet. Now, I'm asking, hey, numpy, what address do you have in your memory in that space? And numpy says nothing. Why? Because I haven't initialized it. So in principle, I cannot do this at this stage because numpy doesn't have a valid address in it. And I cannot say, okay, go to this address and actually find the thing and put this 3 in there. This is what this is saying. This is saying that take 3, number 3, go this numpy and look at what address it has, go to that address and copy this 3 onto that address. But that address is not defined. Why? Because I haven't initialized it. I haven't initialized the value of numpy. Numpy doesn't have anything initialized yet. It may be 0, then I may need to go to the address of 0. So this is not possible. I cannot actually do this thing without this. If I did it afterwards, what would happen? Let's say that I do it here. At this line, I'm saying this one, numpy equals num. So this says take the number num, whatever in num, which is 3, put it where star numpy is pointing at. Where is numpy is pointing at? To the same place num is pointing at, right? So this means that I'm copying the same number to the same place. So this is saying take this thing. So this is num, this is numpy. The address here is 954, right? So go here, take the number, and then copy this number over where this is doing the. So you copy it here again. So you are copying 3 over 3. So this is not the same as this one. They are not the same. They are not the same. One is you are copying the address of num into numpy pointer variable. In this one, you are copying the value of num to the place where numpy is pointing at. So I hope this is clearer for who was the who was the question from? From Eren or Bahadur. Okay, now, so Bahadur, the answer is no, you can't, they are not the same thing. They are completely different things. NumPy is actually, the first one is copying a number to where NumPy is pointing at. The second one is actually taking the address of num, where that value is in memory, finding that address and putting it in place of NumPy so that we can actually indirect access that place again later on. Right. So another question that you have, Eren has, he says NumPy assignment num -1. Wow, good question. So in principle, yes, and we are going to talk about this now. All right. So the question is, okay. I'm going to talk about the answer to this question in depth in the next several slides. I'm going to handle this one. But there is a question from Yaz. He's saying that can num be actually pointing to address that I define? Okay, this is a good question as well. Let's actually get this out of the way first of all. So the question is, right now the num is the address of num. Where is it? How did I get actually this address here for this guy? How did I get it? Compiler gave it to me. Compiler at runtime said, okay, oh, this guy needs a num integer, which is named num. I'm going to give him an integer in memory. And then he needs another integer pointer numpy. And I will give him in memory this as well. All right. So in memory, we'll say, okay, here is some things for your num. This is where your num is going to be. And then this is your numpy is going to be. All right. So these are the memory that it will allocate. The coder, the programmer, will have no way of knowing what this address is going to be. It depends on a lot of different things, but it is not a thing that you should worry about knowing. This is compiler's doing. Compiler will worry about it. Why? This is from the beginning, this is what we have been discussing, if you recall. This is the abstraction that the language is going to give you. If you need to know about the details of this, you need to define, oh, I want to put this at 10, location 10 or location 11 or location 12. This doesn't make any sense because you don't know what locations available to your program at any given time. This is between the runtime engine and specifically the operating system. It is up to the operating system. All right. So this is one thing. Now the second thing is that if I let you do it, if compiler lets you do it, you can put it anywhere. Now you have to know actually how the addresses are actually, let's say, allocated. And this is a big no-no, because if I let actually programmers to do this one, maybe, first of all, I'm actually breaking the abstraction, purpose of abstraction. I'm just violating it. That's the first thing. It makes my job more difficult to do because I need to know where I put this variable and where I put the other variable and so forth. These are very difficult things. Another one is from the security perspective, I may mess up things very, very easily. So memory management, meaning decision of where a certain variable or certain value is going to be placed in memory of your program, is all up to the compiler at runtime. You have no control over it. You will never ever have a control over it. You are not going to say, I want to put this, I like the memory place 10 very much, and I want to put my first variable always in that position. No, there is no such thing. You cannot do that. This is all managed by the compiler at runtime. You have no control over where you actually put them. Okay, so the answer to that question, I think it was Who was the question from? From Yağız Hakkı. The answer is no. You can never ever actually define the address where this thing is going to be put. Now, there are two types of variables or addresses that you can claim from your from the compiler. The first one is what we did here. This is the first type. I declare a variable. When I declare a variable, a local variable, right? Compiler is going to give me a space in the memory for that. It's guaranteed. If it cannot find it, it will not able to actually run your program at all. So this is the first place. The second place is going to be, this is called, this is a specific part of the memory that will be used for this purpose, for this type of declarations. This is the static declarations or static memory allocation. Now, there is gonna be, the next step is gonna be, I need something for dynamic as well, meaning I wanna be able to do this on demand. At runtime, I wanna say, okay, hey, compiler, give me, let's say, 5 megabytes of space for my use, okay? C does that, C helps you do that, but still C decides where to get that 5 megabytes of memory from, or where to place that thing, or where to allocate that thing. The address of that all is defined or selected by C, not by the programmer. So programmer will never ever be able to change where things have to go. Compiler will decide that. However, with this operator, this ampersand operator, I am able to know where that address is. Compiler will not let you choose that address, but it will, once it is actually allocated, it will let you access that address. It will let you know what that address is, and this is what exactly we are showing here. This is the compiler's choice for that num, where that num is actually, where that number 3 is stored. Okay, good. So let's see, there was another question. Okay, int num3, int num, yes. The answer to Muhammed Bedir's question is yes, you can do that. Even though it's not a very, no, it doesn't do that. You need an ampersand sign. So in your second line, Muhammed Bedir, your second line, this line here, I hope you are seeing it, you need an ampersand in front of num. No, okay. No, this is wrong. This is completely wrong. Okay, so let's come back to this one. So he's saying that he's initializing. This initialization says that this has to be initializing the integer pointer. So it has to be the address of num. It cannot be num itself. It can be the address of num. So if you put an address here, then you are fine. All right, so let's continue, and Eren's question is going to be answered, hopefully. So let's look at this code. I have another code. I have an array here. How many entries do I have in this array? 6 entries. I initialize an integer array. And then I have a pointer, an integer pointer, AP. All right. So let's look at the first lines of code from 8 to 12. So 8 to 12 is doing very simple. It says, okay, what I want to do is I want to print the entry A0, the first entry, this guy. How do I access that? Simply A within square bracket 0. All right, so this is easy. We know this one. All right. Now, in the second line, line number 9, the next line, I'm actually printing this A star. Okay, what is this? Now, what happens is that when you do a declaration like this is what C does. For C, actually, if you recall, this was very similar to this one, right? Integer A. when we sent this to a function, for example, we were using it using this convention to send a function, to a function. So what does happen here? What happens here is this, simply is this. So let's do it this way. So this is my memory. When I do the declaration A is indeed a pointer. All right. But it is pointing, it's a special type of a pointer. And it is pointing to an array, in this case, 6 entries. 1, 2, 3, 4, 5, 6 entries here. So it is pointing to here. A is a pointer. Actually, you can think of A as like this. A is a pointer, integer pointer. A is an integer pointer, and there is an address here, some address, and this address is where your value is actually kept, like this. Okay. Now, this definition says A is a pointer, but it is pointing to, it's a specific type of a pointer. It is pointing to, it's an array, and it is pointing to an array of 0, 1, 2, 3, 4, 5, 6 entries. All right. Now, this means that since A is a pointer, I can actually just say A this. A is a pointer. Star means indirect access. What does it mean? Go to the A, the address of A, which is pointing to this place here, 0, 1, and 2, and then take the integer number from there. What is that integer number at A? It's in the beginning. This is the first one, which is 0. So this will print 0. You can see here, it prints 0. Okay. This one prints the second one, the second entry. Now, if I actually take this guy here, A, right? A is a pointer. If I just say, okay, I want to look at I want to increase A by 1. So I have a pointer, and I am trying to increase the pointer by 1. Now I know that this pointer is an integer type. So the plus operator says I have in front, on my left, I have a pointer. And this pointer is supposed to be holding an integer. It's an integer pointer. It is supposed to be holding specifically, it is holding an address that points to a place where I have an integer. Okay. What does +1 mean in this case? +1 says, okay, if you are holding an integer pointer, A is holding an integer pointer, then +1 means that I need to actually look at the next place after A, the current location of A. After that, I look at actually the next place where an integer value can be held. So the next integer pointer, this means the next integer pointer. So this means that in memory, if I had, let's say, let's go back to here. If A is pointing here, this is an integer, let's say 0. The second integer is 1, third one is 2, and so forth, right? 3, 4, and 5. Each of these are how many bytes? 4 bytes in this case. Now, if A is pointing to this, A +1 is gonna point to this guy here. This is A +1. This is A +5. And now, if A +5 is pointing to this guy as an address, the indirect thing, star, putting a star in front of it, should get me the value in that address, which is 5. So these two things are actually doing the same thing. A1, A within square bracket 1 is saying they get the first entry. A +1 and indirect access to that indirect value of A +1 is indeed the second entry of that array. Why? How do I know? Because I will increment A by 1, but I know the type of A. A is an integer address. So since integer addresses have 4 bytes, integers have 4 bytes in it, the next integer address should be 4 bytes away from that first integer. So indeed, what is happening is that A plus 1 is going to refer to probably in bytes 4 more value than the first one, which is, we are going to see it here in a few minutes, and down in the line 17 and so forth. But the basic idea is +1 says that whatever the type of the pointer is, I'm gonna look at the next value that could be after that, the next value and the next value. So every time I increment it by 1 or by 4 or 3, whatever, I'll be actually going, let's say, entry-wise 1 at a time. So if this was an integer A like this, so if this was, let's say, 1, 2, 3, A plus 1 means in address space 4 more than A itself in bytes. Whereas, for example, if I had int, let's say C, and let's say A, B, and so forth, then C plus 1 means whatever C is referring to, let's say address 100, C plus 1 is gonna be 101. So if C is 100, the address C, then C plus 1 is gonna be 101. Whereas if A is, in this case, let's say 100, A plus 1 is gonna be 104. Why? Because integer pointers require 4 byte space from one to the next one and the next one and the next one. Whereas a character, I did it wrong, sorry. This should be character. A character pointer will require only 1 byte increments. If you had, for example, a double array there, then double pointer will require 8 byte increments. So every address after A plus 1 or C, for example, A plus 1 would mean incrementing the first address of A by 8 bytes or 8, number 8. Okay, now let's see how it is happening here. This is now clear. So if I put, for example, here 3 instead of 1, what would I get in this line here? This is this line here. So if I put 3 there, 3 on line 11, instead of A plus 1, I put A plus 3. This will not affect anything here, but it will affect this guy. What will be the result of this one? Someone tell me. Can you tell me? Will it be still 1? No, because I'm saying, okay, hey, A, where are you pointing at? You are pointing at currently 0, entry 0. And I'm saying, okay, I want to look at 3 after 3 place further than where you are pointing at in integer things. So this is A, this is 1 place further, 2nd place further, 3rd place further than that. So it will actually print here 3. All right. So we can see this in another way here. So what I did is I actually said, okay, let AP, the pointer, integer pointer, be A. I can do that because A is a pointer, AP is a pointer. I can assign, and they are the same pointer, same type of pointers. One of them is integer, the other one is also integer. So I can copy A to AP. Now, what I'm going to do is, if I actually look at AP here, the address of AP, the first one, and whatever is contained in that address. So you can see that apparently the address of AP, which is this guy for the time being, is something 7FFD1, whatever, 28E0. This is hexadecimal, be careful. And the value that I am going to be printing is the AP, the value at this address is 0. So means that the address of this guy is this one. So what if I actually increment AP by 1? Okay, now as before, the increment operator is going to say, okay, you want to increment me, meaning the AP? Yes, I want to do that. So how am I going to do it? I'm going to look at, what are you? Are you an integer? No, you are not an integer. Are you a double number? No, you are not a double number. What are you? You are actually, AP in this case is an integer pointer. So it means that for an integer pointer to be actually incremented by 1 means I am going to actually, the current value of this integer is this guy here. Pointer is this guy. The current value is this guy. 28E0 for last 4 digits. Plus 1 means, or incrementing it by 1 means, I want to actually increment it and look for this next integer after you, which is 4 bytes away from you. It cannot be just 1 byte away because your type is integer. So each integer keeps 4 bytes, 1, 2, 3, 4 bytes. So the next one, so this is the first one here. This is A. A plus 1 is gonna be, or A plus plus 1 is gonna be 4 after this one. So skip this guy, skip this guy, skip this guy. This is 3, skip, and this will be it. So you can see that the one increment caused AP to get the value from E0 to E4. Right? Perfect. And this is gonna be this guy. It is clear. Now, when I do another AP plus operator says, post increment operator says, okay, take the value of AP. I know that it's an integer address, integer pointer. The next integer would be 4 bytes away from the first one. So now you see that the next increment is now, instead of E4, it is E8. It is incremented by 4. So this thing is incrementing AP by 4 at a time, not 1 at a time. Why? Because the increment operator says, I am going to actually increment you such that it depends on your actually what you are pointing at. When I'm going to say, okay, when I increment you, I will make sure that you point at the next number, the next value, the next value after you. So, all right. So that's why I have it that way. If I change this thing, for example, to character, what would happen? So if this is 0, this guy is gonna be 1. Why? Because characters are 1 byte. They are 1 byte. Their length is 1 byte. So this AP plus plus is gonna say, okay, you are a character pointer. The next character will be 1 byte away from you, not 10 bytes away from you, not 2 bytes away from you, but 1 byte away from you. All right, therefore it's gonna be, and this one is gonna be 2, 1 byte away from you. All right, what if this is, let's say, a double or a long integer? So these are long integers. So if this is the case, what will be this guy here? Someone tell me, what is the number gonna be there for the first increment? 0.8, exactly. Why? E0 is your current position. Increment operator says, okay, I want you to actually point to the next number. What type of a number are you? You are, I know it from your pointer. Your pointer says you are a long integer pointer. And I know that long integers are 8 byte long. So your current location, if your current location is 0, your next entry, your next value after you should be 8 bytes away from you. And the next one 8 bytes away from that one, and next one 8 bytes away from that one. All right, this is good. So what if I have something like this? Let's say, forget about this part for the time being. Okay, what if I change this one to empty my type, and my type is something like this: type def struct, and let's say integer A30, character S50, and that's it. And this is my type. So if this is the case, incrementing from here to the next one, what would be the next one? How do I know it? So my type is empty now, not integer, nothing. So AP++ is gonna say, where are you currently? E0, location E0. I want you to point to the next value, next value that includes what? An integer array and a character array. How many integers in the integer array? 30. How many characters in the character array? 50. How many total bytes do I need for this guy? Someone tell me how many bytes? 170. Let me see. 30 times 4, 120, plus 50, 170. So I would actually have here, in this case, this guy is gonna be whatever 28E0 plus hexadecimal. This is hexadecimal. Whatever the hexadecimal correspondence of 170. So I will add 170. I need to convert to the hexadecimal number, but it will be away from 170 away from your current position and so forth. Now, this is very interesting now. I am able to actually now kind of do funny things, fancy things, not funny necessarily, but fancy things. Like what? Let's look at it. I have the same array here. I have an AP, which is a pointer, integer pointer, the same type as the array. And I have an I here, integer. For example, now I can actually do this one here. This is going through this, the array. And what I'm doing is I'm actually showing you this one here, AI, the address of A plus I. And you can see the first address is 0, B0. The second one is B4. So A plus 1 is 4 away. The third one is 8 away, and another 8 away, another 8 away, and another 8 away. This is good. And these are the numbers that I can reach at that location. Just take this A plus I and do an indirect reference to it. So get the indirect value of it. Good. This is kind of, this is the same as doing AI like this. Okay, fine. Let's do a little bit fancier stuff. This one. What I do here is that I do another for loop, but this time I'm saying, okay, the start of it is actually my counting variable is AP, an address, and I initialize it with the first, with the fourth entry of this array. Take the fourth entry here and then get the address of that fourth entry. So what will be the fourth entry address here? Look at this one, this guy. This is the fourth entry, 0th, 1, 2, 3, and 4. The entry 4, this is my starting entry. This is AP, okay? Go till where? Do this iteration till you are still larger than or equal to the address of A. Meaning, go start from here, and I'm gonna probably do a decrement. Go from here and then actually go one here, another one, another one, another one, and stop there. So start from the fourth entry, go one at a time down till you reach the 0th entry, and after processing the 0th entry, finish your loop. And you can see it here that this is exactly doing what I described to you, that it starts from the fourth entry, the third, second, first, and 0th entry, and actually it is putting the indirect value of that. Indirect value of that AP is exactly fourth entry, first, third, second one, and 0th entry. Questions? Any questions? No questions? Oh, we are out of time. Okay. let's take a 10-minute break and we'll continue with this one. All right. See you at 2:40.